Welcome to the Explainer. So today, we're going to jump into a really core concept in statistics, maximum likelihood estimation. Now, I know it sounds a little intimidating, but at its heart, it's really just a powerful mathematical way to find the very best explanation for the data we see.
All right, so let's just kick things off with a simple puzzle. Imagine you flip a coin 5 times, and you get this result: 4 heads and just 1 tail. So the big question is, what do you think is the coin's true probability of landing on heads? Is it a fair coin? Something else? What's your best guess?
Now, to really get a grip on this, we've got to first talk about the crucial difference between two fields that can seem really similar: probability and statistics. They're like two sides of the same, well, coin. Think of it this way. Probability starts with a known fact. It says, okay, I know this is a fair coin. The chance of heads is 0.5. Given that, what's the probability I'll get 4 heads in 5 flips? Statistics, on the other hand, does the complete opposite. It looks at the results first, our 4 heads, and then it works backwards. It asks, given the data I just saw, what's the most likely model? What's the most likely probability of heads for this coin? And for this explainer, we are squarely on the statistics side of things. Okay, so back to our coin problem. We have our data. Let's just go with our gut and make that first, most intuitive guess.
So when you see 4 heads in 5 flips, your brain, which is just an incredible pattern-matching machine, right? It probably just leaps to a conclusion. The best guess has got to be 4 out of 5. That's 0.8 or an 80% chance of heads. It feels right, doesn't it?
But here's the real kicker. Our intuition is screaming 0.8. That's great. But how do we move past just a feeling? How can we actually prove, objectively, that 0.8 isn't just a good guess, but that it is the single best possible guess we can make with the information we have? And to build that proof, we're going to need a special tool. And this tool is the main idea for today. It's a function that gives us an objective score for how good any guess is, and it's called the likelihood.
The likelihood function is actually a pretty simple idea when you break it down. All it does is ask this question. Hey, what if we just pretend for a second that the coin's true probability of heads was some value? Let's call it theta. If that were true, how likely would it be that we'd see our exact outcome of 4 heads and 1 tail? And we can ask this for any hypothetical probability we can dream up.
Okay, and this is where it gets really interesting. We can actually see this in action. So let's say the coin was really biased toward tails, like only a 20% chance of heads. Well, the likelihood of getting our result is tiny, practically 0. What if it's a fair coin, 50-50? Okay, the likelihood goes up, it's more believable, but then look what happens at 80%. Bam! The likelihood hits its absolute peak. It's the highest number on the chart. And then as we go higher, say to 90%, it starts dropping off again. And that right there, that's the big aha moment. The reason your intuition screamed 0.8 from the very beginning is because 0.8 is the one value that maximizes the likelihood of the data you actually saw. Your brain was unconsciously trying to find the peak of this likelihood curve the whole time. All right, so now that we've got the intuition, let's see how we can turn this into a formal, repeatable recipe that will find us the best guess every single time. This whole process has a name: maximum likelihood estimation, or just MLE. And the name says it all, doesn't it? Our goal is to estimate an unknown parameter, in this case the coin's probability, by finding the value that results in the maximum possible likelihood. We are literally trying to find the very top of that likelihood mountain we just saw.
Now, here's a quick but super important point. We don't actually care about how high the peak of that mountain is. That number is called the max. What we really care about is the location on the map, the specific parameter value that gets us to that peak. And that's called the argmax. So in MLE, we are always solving for the argmax.
So how do we find that peak without just guessing? Well, calculus gives us a foolproof recipe. Step 1, you write down the mathematical equation for the likelihood. Step 2, you find its derivative, which is just a fancy way to measure the slope of the curve at any point. And step 3, you set that derivative equal to 0. Why? Because at the very tippy top of a peak, the slope is perfectly flat. It's 0. Solve that equation, and you've found your argmax.
Okay, so that recipe sounds great in theory, right? But in the real world, especially when you have tons of data, that math can get super messy really fast. And this brings us to a wonderfully clever mathematical trick that makes the whole thing so much easier.
You see, the problem is that the likelihood function is just a big, long chain of multiplications. To get the probability of a sequence of events, you multiply, multiply, multiply. Now imagine not 5 coin flips, but 5,000. You'd be multiplying thousands of numbers together, and taking the derivative of that, well, it's a nightmare.
Well, the solution comes from this, honestly, almost magical property of logarithms. And it's the fact that they turn multiplication into simple addition.
And this is a total game changer. Instead of taking the derivative of a horrible product of 1,000 things, we can first take the logarithm of our likelihood function. This instantly transforms that messy product into a nice, clean sum. And taking the derivative of a sum? Piece of cake. It's so much easier.
Now, you might be thinking, hang on, you just changed the whole function. Won't that give you the wrong answer? And this is the brilliant part. The logarithm function is what we call monotonically increasing. It's a fancy term that just means it always goes up. So yeah, it'll stretch and squish our likelihood curve, changing the actual height of the peak, but it will never ever change the location of that peak. And you can see it perfectly right here. On the left, our original likelihood function peaks at 0.8. And on the right, the log likelihood, it looks like a totally different curve, but where's its peak? In the exact same spot, 0.8. So we get to work with the much, much simpler function and still get the exact same correct answer. It's an absolutely brilliant shortcut. So let's just quickly recap the big takeaways here. First, MLE is a foundational method for figuring out the best parameters for a model based on the data you've got. Second, it does this by making our intuition mathematical. It asks, what parameter value makes the data I saw most probable? We find that answer by hunting for the peak, the argmax of the likelihood function. And finally, that amazing log likelihood trick is what makes this powerful idea actually practical to use on real-world problems.
And that kind of leaves us with a final thought. We started with a question that's almost childishly simple, right? Just a coin. But this exact same method, it's the engine running under the hood of so many things that shape our world, from predicting financial markets, to analyzing DNA and genetics, to training the massive machine learning algorithms we use every day. It all comes back to this one powerful idea, finding the explanation that best fits the facts.